Okay, our first question is to find the velocity at the 5-second instant. We know that the initial velocity is 0. The velocity after 10 seconds is 50 centimeters per second. So we know then v of 0 equals 0, and we have a straight line v versus t graph. That's one of the assumptions. That implies that velocity at 5 seconds is half the velocity at 10 seconds because the graph is going to be an instance of this kind of a graph again. It's going to start at the origin, and it's going to go up to some velocity, and we could say, okay, this is 10 seconds, and this velocity is 50 centimeters per second. Okay, so 10 seconds, we've got 50 centimeters per second. We want to know when the velocity, or what the velocity is at 5 seconds, so we just come over to 5 seconds, see that's going to be half of the velocity at 10 seconds, and that's going to be 25 centimeters per second. Another way to think of it is simply velocity is increasing from 0, and it's increasing at a steady rate, so in half the time it's going to come up to half the velocity. So, okay, now, that's very straightforward. What's the position at 5 seconds? Well, we know that the initial velocity is 0, and we know that the velocity at the end of the 5 seconds is 25 centimeters per second, and we know that it's a straight line graph, so for that 5-second interval, the average velocity is the average of the initial and final velocities, which turns out to be 12.5 centimeters per second, from which it follows that your displacement is the product of your average velocity and your time interval, 62.5 centimeters. So our S of 5 seconds is 62.5 centimeters. Now our velocity, our v of t, is what? Well, the graph looks like this. The rate at which the velocity is changing with respect to time is 50 centimeters per second divided by 10 seconds, or 5 centimeters per second squared. If we multiply that by t, well, t is the time that's elapsed since this initial instant. We're multiplying then the average rate at which velocity changes by a time interval, and that's going to give us our velocity. So v of t is going to be 5 centimeters per second squared times t. And we could think of that as just slope times run. From the initial point to time t, we multiply the slope, which, given this information, is 5 centimeters per second squared, and it represents the rate at which velocity changes, or we could call that the acceleration. And we multiply that by the run of the graph, which is just equal to the time coordinate t. We get the rise, and since we started at the origin, the rise is equal to the velocity at that time. And we get v of t, again, 5 centimeters per second squared times t. Now, what's S of t? S at time t is the average velocity multiplied by the time interval. The average velocity for the interval from 0 to t is what? It's the average of 0, the initial velocity, and the 5 centimeter per second squared times t, final velocity on that interval. And that's going to be average. You're going to add those and divide by 2 to get your average velocity. You multiply that by t. Another way of looking at it graphically, it's just the area of this purple trapezoid. If I can find a purple piece of chalk, there we go. So it's just the area of this purple trapezoid. And we could write area 2.5 centimeter per second squared times t. We could say, writing in purple to be consistent with this, in this case the slope is 5 centimeters per second squared. That might not be readable. It says 5 centimeters over second squared.